Pfeiffer, who will tell us about progress on improving the sample quality of gallium arsenide and aluminum arsenide quantum wells.
And you see my slides.
We see your slides, your pointer. Please go ahead.
And my pointer both. Okay, good. So assuming you can in fact see what I'm showing on my screen, this talk will be on some recent, in fact, new progress on improving the sample quality of both gallium arsenide and aluminum arsenide quantum wells, and in fact, gallium arsenide holes and electrons both. My collaborators are shown there, and now we will start. I'm going to move this guy away from me so I can see it better. Over there. So I want to start by emphasizing that this is recent progress in gallium arsenide quantum wells. And it is in fact somewhat surprising that we have new progress in gallium arsenide quantum well mobility, because as you all know, gallium arsenide is really a mature material. There have been 5 Buckley Prizes and the 1998 Nobel Prize that depended on gallium arsenide quantum wells. Because of this history of breakthroughs in physics, many groups around the world over the past 4 decades have worked to improve the mobility of gallium arsenide quantum wells, usually by MBE. But the lesson, I think, of this development is that even after these 4 decades of intense effort on MBE gallium arsenide, there appears to be still room for progress in this important material. So this is the mobility history of the very best quality gallium arsenide quantum wells over the years. And you notice that since about 2000, the history shows a slowdown in progress. There are 4 labs that can do what I consider ultra-high mobility gallium arsenide: Princeton, Weitzman, ETH Zurich, and Purdue, and they've all slowly converged to a best repeatable quantum well mobility in the low 30 million mobility range in centimeters squared per volt second. And the question to start off with that made us think about this is, why have all these labs become stuck at what is essentially the same place, and what can we do to fix that? And the first point that occurs to us is that these samples had various electron densities. The Gossard sample in 1986 had a density of 1.6 10 to the 11 electrons per square centimeter. Our 88 sample had 2.4 10 to the 11 per square centimeter electrons, and the 2 samples in 2000 and 2007 that we grew had densities around 3 10 to the 11. So the density has been creeping up. So let's, instead of looking at just the very highest mobility samples, let's look as a function of density, what are the highest mobility samples? And so this is a plot on which the horizontal axis is the density of the 2D electron system, and on the vertical axis is the transport mobility. And what amounts to, there's a red line that I'm trying to draw through a bunch of data points, all of which happen to be our data points, but other labs could fill in other points on that line. And I think this red line is representative of the best quantum well mobilities versus electron density that have been achieved worldwide between, say, 1998 and 2018. However, in May of 2019, we began to grow some low density quantum well samples with electron mobilities that clearly seem to be off above that red line. And so we became very excited at our progress after 30 years of trying. And by October 2019, we grew a series of better samples that were even, and we mapped out what we think is a new higher mobility regime. And just for the technical records, we varied the setback by silicon doping from both sides to control the density of a central quantum well. And we essentially varied the well width, always maximized it to just avoid populating the second subband. So the thing to take away from this view graph is that for electron densities between about 310 to the 10 and 1.2 10 to the 11, we achieved a factor of 2 higher mobility across a whole series of samples. But we interestingly find that the density versus mobility slope is preserved. It's 0.7. It's the same as the red line, in other words. Then at the very highest densities, the data points fall off this 0.7 slope. And this tells us that there's a different issue affecting the 2D mobility in that regime. However, the peak mobility does reach 44 million at a density of about 2 10 to the 11. So that's an advance. The nice canonical point is at density 1 10 to the 11, the best mobility on the red line, and the previous that we were able to achieve, and I think elsewhere as well, was 18 million. And now we can do 36 million at density 1 10 to the 11. So it's an advance. So then we wanted to look at what effect that had. And these samples, these new samples, which were available to us in 2020, we looked at low temperatures and published the result in Nature Materials in January of this year. And you'll see that we see 10 additional quantum Hall states in red shown here that were not observed before at any temperature. So that the mobility is really reflected in better quantum Hall spectra. Also, near zero field, we see Shubnikov-de-Haas onset. We see 106 oscillations, but the key thing, I think, is that we see the onset of the oscillation starting about 370 Gauss. And our earlier samples always showed oscillations above 700 Gauss. So there's a factor of 2 in the quantum Hall quality as well. Then the graduate students, Chung and Villa, made a study of the gap. And we measure an energy gap of that 1 times 10 to the 11th state at the 5 halves filling factor. And we find an energy gap of 820 millikelvin, which is higher than the old records. And what's interesting is this was all achieved at 110 to the 11 density, whereas the older record at 608 by the Manford group was at a much higher density of 3.4 10 to the 11. So a higher gap is useful in the 5 halves quantum state, and this should improve the signal to noise ratio in quantum interferometer experiments such as those of Willett. But in addition to this, we've made progress elsewhere. And so in early 2021, January through April, we grew a series of quantum wells containing 2D systems of holes. And here too, we've made some serious progress. If you look at this spectra, we can see states out to 8/15. This is a hole, a sample of 2D holes. Again, doped from both sides using 32% barriers and 16% near the well, sort of a stepped setback. But we see a mobility of 5.8 million on our best sample and many samples above 4 million, like 6 or 7 samples above 4 million. And this is at a density of 1.3 10 to the 11 holes per square centimeter and measured at 280 millikelvin. So that improves the old record by about a factor of 4 for holes. And for low density holes, at very low densities, here's 410 to the 10, we even see 3.6 million mobility at 280 millik. We see a nice 1/5 state, and we see the mobility of 3.6 is vastly higher than the old records we were getting for holes at that density. So that's good. And finally, to complete this picture of mobility progress, we review our published 2018 progress with aluminum arsenide quantum wells. And the red points are the new regime of aluminum arsenide quantum wells we did in 2018. And these exceeded the best previous samples by about a factor of 8. You can see the blue points at the bottom. And this is to show you that the in two different samples at 100 millik, how beautiful the fractions look around 110 to the 11 and 610 to the 10, where we see a nice 1/5 state. So when I look at these, if you just glance at them, you would not recognize them. You think of them as gallium arsenide level quality. So the question you must have in your mind then is, how are these mobility breakthroughs accomplished? And so in the remainder of this talk, we're going to focus on the changes that we made to our MBE growth procedures that enabled this progress. And there are three things we did. We installed novel 18 Kelvin cryosurfaces in the vacuum sump of our MBE system. We developed a new method, which we think is highly sensitive for evaluating the relative purity of our barrier material, or AIGaAs barrier material, on either side of the quantum well. And then we leveraged this method of high purity step that we just talked about, step 2, to improve the quality of our MBE vacuum itself. When you can measure something, you can often improve it. We demonstrate that. So to show you our system, we built the system we designed and built the system over the years 2011 through 2015. And when we did that, we put in some modifications. We put 4 externally valved cryo pumps right there around the base of the thing. We call this region here the sump of the MBE machine. So we had 4 external valves cryo pumps there, charcoals at 11 kelvin. We also installed large area cryo pump plates, cooled plates that cool this copper surface to 18 degrees Kelvin, and a second one that cooled a little finger sticking into the growth environment at also 18 degrees Kelvin. And so then we started working on that in 2015. And it actually was a technique, these new plates, these 18-degree cryo traps were really a technical success because they reduced the ambient impurity levels that we measure every day in our residual gas analyzer. And so if we leave the internal cryo plates at room temperature, we see a nitrogen peak, an oxygen peak, 2 water peaks, and another nitrogen peak or a CO peak. And if we turn on these pumps 2 hours later, the peaks all drop by factors of, in the case of nitrogen, by factors of 10, oxygen by about a factor of 10, and the water peaks by a factor of about 2.5. If we let the pumps go on for a week or more, even the water peaks disappear beyond our ability to see them in the residual gas analyzer. So this was clearly a big technical success because we could reduce the known impurities in our machine. But in fact, the cryopumps did not really improve our gallium arsenide quantum well material in terms of mobility in the years 2015 through 2017. So it was a disappointing thing. And disappointments sometimes make you think a little harder. And so to see a change in quantum well mobility, we had to solve another issue, which we didn't realize we had. We need to characterize the purity of our AIGaAs material that we grow. And our first understanding of this AIGaAs impurity problem was to realize the importance of the barrier itself, this AIGaAs barrier on either side of the quantum well. And we did this by studying the quantum well mobility as a function of the thickness of the lower barrier that forms the well. We can vary that lower variance between a triangular well and a real AIGaAs barrier. So here's what I mean by that. So it was a historical kind of accident in a way. In 2017, we had run out of aluminum in our cells. And so we opened the machine very briefly and we filled the aluminum cell with new material. But the gallium was fresh from a previous campaign. And so we decided to think about running it in that mode. And so the machine had a gallium charge that we thought was clean from the previous campaign, but the new aluminum charge was clearly full of impurity atoms from the inadequate refining that's done on aluminum, and the oxide overcoats and things. So then we grew a series of quantum wells that we remotely doped from above, and we measured the transport mobility in these wells as a thickness of the lower barrier located just below the well, and we saw a dramatic result. So here's our data. So remember now, this has got what we think of as dirty aluminum to make a likely dirty aluminum gallium arsenide barrier. And if we didn't put that lower barrier in at all, we saw 9 million mobility. It was just a triangular well doped from above. And if we inserted 60 nanometers of AIGaAs at the bottom as well as at the top, we saw only 1 million mobility. And to show you schematically what we're talking about, here's the top case where the 9 million is just a triangular well. If we put a little thin lower barrier of 10 nanometers, we get 5 million. So it dropped at a factor of almost 2. And if we made that barrier thicker to 60 nanometers, it dropped it all the way down to 1 million. So this was the biggest surprise in this was just by varying the thickness of the lower barrier, we see some continuing decline in the mobility. And the question we just think what was happening here. And as a clue, I want you to think about the direction of the MBE growth. It's growing from the right side toward the left side in the direction of the red arrow. So let's proceed. The degradation in that AIGaAs barrier below got better if we exercise the aluminum cell. So what we did is we just baked the aluminum cell offline for about 200 hours at its run temperature. We just had a junk shield, and we just dumped the aluminum cell on weekends and over a vacation time for 200 hours onto that junk shield. And the mobility from the lower barrier after that offline baking was concerned. We didn't do any other baking in the system. It rose from 1 million to 5.5 million, that little arrow there. We did another bake, this time 40 degrees above the aluminum run temperature. The first bake was just at the aluminum run temperature. The second bake was 40 degrees hotter, and it was only 125 hours long. And it cleaned up even more. So now the 60 nanometer lower barrier isn't really affecting the mobility at all. It just stays flat. And if you do a third bake, this time 80 degrees above the aluminum run temperature for 90 hours, the cleanup occurs even longer. So what can we conclude from this? These experiments showed to us that the quantum well is becoming contaminated by impurities from the AIGaAs barrier located just below the well. In other words, the gallium arsenide, no matter how clean it is getting impurities from the barrier material that's located just below the well. The quantum mobility decreases as the lower barrier gets thicker. And this suggests to us that the impurities are moving through the lower AIGaAs barrier toward the quantum well. And this mobility degradation is reduced as the aluminum diffusion cell is baked offline. That's just because the aluminum is the source of the problem, as we thought before. And if we bake it offline, then the aluminum is producing producing fewer impurities, and these impurities aren't incorporating in the lower barrier. So that's the experimental facts. But this fits a model that we think of, and the model is called surface segregation. And the impurities associated with the aluminum cell are chemically bind with the aluminum atoms in the growing lower barrier, AIGaAs lower barrier. And then that lower barrier becomes impurity contaminated. When the impurities land on it, they delay incorporation because impurities don't like to fit into the lattice of the AIGaAs. They're usually out of place. So more aggressive aluminum atoms or even gallium atoms can take their sites, and this causes the impurities to drift upwards towards the growth surface. They just try again at the next monolayer and the next monolayer, and they drift upwards. And this method is called MBE-Surface-Segregation. Finally, when the AIGaAs lower barrier is complete and the growth of the gallium arsenide quantum well begins, the impurities all of a sudden face less competition for lattice sites. Now they don't have to fight the aluminum, they just have to fight the gallium for sites. And so they quickly incorporate into the gallium arsenide quantum well. And we know that impurities in the quantum well strongly degrade the channel mobility. So we have some evidence for this little model of impurity surface segregation. And those things are going to show you next. So the first thing I want to show you is some SIMS data. SIMS means, in the MBE parlance, secondary ion mass spectrometry. So imagine a beam of cesium up in this corner. So there's a beam of, say, cesium atoms, and they are energetic beam, and it digs a hole in the gallium arsenide and goes through that, and then digs a hole into the AIGaAs barrier, et cetera, et cetera. And this is a picture then. And what's captured from the cesium beam is the cesium atoms are ignored, and we look at all the gallium atoms coming off, all the arsenic atoms coming off, and all of the impurity atoms coming off, and the aluminum atoms coming off. So this red curve is the aluminum atoms coming off. And that's the lower barrier. In this case, that was 400 nanometers wide. So what you see then is the impurity, we had to guess as to what it was. And we looked for both aluminum and carbon, which are likely candidates. And not aluminum, we looked for oxygen and carbon. And so the oxygen does indeed show this sort of buildup. You can see it on the log scale very nicely, where it's snow plowing up more and more and more oxygen. And finally, at the end of the lower barrier, there's a huge incorporation peak into the gallium arsenide below. And this occurs, as I said, because now that there's no aluminum atoms to compete with it, they can incorporate very quickly in the quantum. And this lower trace just shows you the same thing happens, but after the aluminum cell is baked, and you see that the entire experiment is much more quiet, but it's still there. There's still the same problem occurring. So that's some evidence that this model might be correct, surface segregation. The other is that we substituted for the lower barrier, which is, you think of as just a monolithic aluminum gallium arsenide barrier, one big thick barrier. But instead of that, you can in fact make the barrier up using a superlattice of 30 angstroms of gallium arsenide, 100 angstroms of ALGaAs, and repeat that. If you do that, the entire effect goes away, and there's no degradation at all, no matter how thick you make that layer, this red line. And the reason is that the 30 angstrom gallium arsenide healing layers actually incorporate all the impurities, and so they don't ever build up and to make a problem. So there's no more snow plowing effect. So this is a classic example of a way to suppress surface segregation as a superlattice. And so that made us think that our model again is correct. So rather than suppressing the MBE surface segregation, we decided to try to use it and make it as a tool. And from that tool, we could infer the impurity content of the AIGaAs itself. So this is the same SIMS data that you saw. And if you look at what's happening, you see what's happening is over 400 nanometers in the lower AIGaAs barrier, there's a buildup of impurity, oxygen impurities going like that. And so it's collecting things for 400 nanometers and essentially dumping the oxygen atoms, and it's dumping these impurity atoms right in this 100 angstrom or 10 nanometer space right here. So there's a gain of factor of 40, 400 to 10. So we've got a factor of 10 gain of the impurity. We concentrate the impurities right at the gallium arsenide quantum conducting layer. Now I know from other work over the years that I've done is that if we put 10 to the 15 atoms of impurities of any kind, we can lower the transport mobility in a clean quantum well from about 10 or 12 million to 1 million. So if you combine these two figures, divide 10 to the 15 by 40, you get 2.5 10 to the 13 charged impurities in this lower barrier can lower the mobility from 10 million to 1 million, which is in fact is what we've been seeing. but it gets more interesting because we can actually see how thick the lower barrier can be made. And this time we extended the lower barrier's thickness from 400 nanometers all the way to 4 microns, another factor of 10. And clearly now, the effect of MBE surface segregation is still operative. The impurities are swept from the entire lower barrier and concentrated into 10 nanometers. So now we have a factor of 4,000, and that that makes the sensitivity of this effect go up to on the order of 310 to the 12 impurities per cubic centimeter. So our conclusions are that a thicker lower barrier implies higher ALGaAs impurity. And so we can use this sensitivity to qualify our barriers to an ultra clean level by just cleaning up the aluminum cell. And we then extended it a little bit further, and we can use the same ideas to characterize the quality of our MBE vacuum pumping, as you'll see next. So now I'm showing you the plots that I want you to concentrate on this blue line. This is our standard MBE system where the 4 cryopumps externally valved are operating, and we don't have any additional pumping of any sort, no internal 18 degrees Kelvin seats or whatever. So the first thing we did then is we're going to either take away pumping or add pumping and see if we can see any change from this blue line. The first thing to notice, though, is that the characteristic thickness now is 3 microns, 3.1 microns, where the mobility drops to essentially half of the value. It's just like the point where the barrier is, where the lower barrier is giving us trouble to the extent of killing the mobility by a factor of 2. So if we have 1 cryopump instead of 4 cryopumps, we just turn the other 3 off and close them off. We see that the orange triangles, the half point drops all the way from 3.1 to 2.4. This says that pumping with 1 cryopump causes more impurity contamination in the lower barrier than when we use 4 cryopumps. So we can make things worse by just turning 3 pumps off with 1 cryopump versus 4. So the question is, can we go the other direction? And that works too. This time we turned on, in addition to the 4 cryopumps that we had, we turned all 4 back on. And this time we added the 18 degree Kelvin cold plates in addition to the 4 cryopumps. And those are those points. And now you see it goes all the way to 5.9, the half point from 12 or 13 million down to about 6 million. This experiment shows that the 18 degree Kelvin cold plate improves the ALGaAs lower barrier purity by a factor of 2. Our rule of thumb is if it takes a thicker barrier, if it's cleaner, and if it's very dirty, it takes a very thin barrier to cause all kinds of problems. So in summary, I think we've shown the following thing, that the impurities can drift into the conducting channel of the gallium arsenide quantum well from the lower barrier by surface segregation. And that causes, that's a characteristic thing limiting in the past the mobility of quantum wells in gallium arsenide. In many MBE systems, the impurities in the barriers arise by capture from the outgassing of a not optimally baked aluminum fusion cell. But in fact, in very clean systems, the impurities are still in the aluminum arsenide barriers, but this time they arise by capture from the general MBE ambient. But we can clean that up too by these cryotraps. So by cleaning up the MBE ambient with our huge 18 degree cryotraps in the sump, and by proper fusion bakeout, we can improve the impurity of the lower barrier material. And this dramatically improves the mobility of the ALGaAs of the gallium arsenide quantum wells. Well, we can improve the mobility of aluminum arsenide quantum wells or electrons and holes in gallium arsenide quantum wells. So all of the advances, I think, hinge on this little slide. And so we think we understand why the impurities, why the breakthroughs happened. And with that, I will thank you for your attention.
Thanks very much, Loren, for the nice